this is the first lecture on the tangent, normal, binormal, curvature, and torsion calculations. The way I'm going to do this is start off on this lecture with the arc length parametrization. And this, using the arc length, calculating these vectors and these the scalars, the curvature, and the torsion is the easiest. It has the fewest parameters involved. Then the next lecture, I'll do the same thing for arbitrary parameterization and show that you get essentially the same results. All you need is to multiply by the magnitude of the velocity. You get the same results. Then I will apply this to a couple problems in mechanics and then apply it also to the helix. Stewart and Thomas sort of spread these calculations out over several sections. What I'm going to do is just trace right through the calculation, and I think you will see how how easy it is when you look at it that way. Then after you get the calculations and the pattern of creating these vectors, you can start to explore what they mean and various implications of them. I'm going to start here with a motivation for these T, B, and M frame by looking at a roller coaster. Almost frightening just to look at it. But let's say you are sitting right here. You're riding the roller coaster and you're right here. Well, what is the thing you're going to care about the most? You are not going to care that somewhere over here, perhaps at the base of this thing or at the beginning of the amusement park, is the origin for some IJK coordinate system that tells you where you are. Instead, you're going to care about three other vectors. You're going to care about the direction of your velocity. You're going to care about the direction you're going, and that will be a direction that's exactly tangent to the curve at that point. So if you came loose of this roller coaster car, this is the direction that you're going to fly off in. That's important to know. All right. The next thing you're going to care about is how you're turning laterally. It doesn't matter with respect to the ground. It matters with respect to the direction your eyes are looking or the direction your shoulders are facing. You want to know how you're going to be turning laterally with respect to that, and that's usually described by a vector in the direction of the, you see how the curve is going? Okay, there's another vector pointing directly in that direction. That's the normal vector. That's describing this change, this lateral change. And because this is a three-dimensional roller coaster, you're also concerned with whether you're being pulled up along the roller coaster or whether you're going down. In this case, it looks like you're going down, so there's another vector that describes that. So here's your tangent vector, there's your normal vector, and here's what's called the binormal vector. Now, at every point in the roller coaster, these change. For example, over here, your tangent's probably going off in that direction, normal's in this direction, and the binormal, I guess it's probably going here because I think we're still going down. So here's the T, N, and B vectors at this point. So you can think of these three vectors as forming a unit vectors of, in a sense, a coordinate system, and it's going to move with you as you move along this roller coaster. There's two other coordinate systems that sort of act like this in that they translate with a point, and that is the cylindrical coordinate system and the spherical coordinate system. But you don't want to use those because, for example, they might apply, say the spherical applies really well when you're over in this region, but how about when you're traveling along here? This is a straight line, and spherical coordinates are really not very good to describe the motion here. So instead, you develop that T, B, and N framework at each point as you go along on the space curve. There are two other scalars that describe the properties of the curve at each point, and one is a curvature, and the other is the torsion, and they also are related to this T, B, and M frame. The T, B, and M frame are also used in computing the velocity along a curve, the acceleration, and the forces. And in the lecture on mechanics, I'll show you how that's done. Throughout all these lectures, you're going to see the same thing happen over and over again. And it's that you have an arbitrary vector, and you break it up into its magnitude and a unit vector in its direction. If this vector v happens to be velocity, then the magnitude is the speed, and the unit vector is a unit vector in the direction of motion. For the derivations here, the vectors will be calculated by taking successive derivatives. Then each vector will be put in the form of a magnitude and a unit vector. The magnitudes will have the names curvature and torsion, and the unit, well, now I've messed up my color scheme, didn't I? Well, the unit vectors will have, are named the t, the tangent vector, the normal vector, and the binormal vector. These will be unit vectors, but they are not written with hats. You know, we usually write I with a hat on it or K with a hat on it to signify a unit vector. The hats are left off, but they are unit vectors. So they come from that part of the vector, and the curvature and the torsion. Let's see if I can make this. No. Alright, well, I've messed up my color scheme here, but the curvature and the torsion are the scalar magnitudes. These vectors and the scalars kappa and tau are properties of the curve that don't change when you change parameterization. You know that you could have the same image, the same space curve, and it could be parameterized by say some parameterization that moves along the space curve and describes it very rapidly, or one that describes it very slowly, or one that goes from left to right or right to left, or you could have the arc length parameterization and the image of that curve would be the same. Now these TBN vectors and the curvature and the torsion are also the same along those curves, and they're called the invariance of the curve, and that's another reason why we compute them. To give you an idea of what this curvature is, curvature measures the nonlinearity of the curve. If you think again about the roller coaster, it measures how you're moving laterally. So if you're moving along a straight line, you're not moving laterally at all. In that case, the curvature is 0. For some curves, such as a helix or a circle, the curvature is a constant. But in general, the curvature varies as you move along the space curve. If you had a real tight corner here, and then you took off again. Right in this region, the curvature is essentially 0. But in this corner, you would have very large curvature. The torsion is related to that binormal vector, and I keep grabbing the wrong thing, sorry. And it tells you how you're pulling out of the plane. If you think of a helix is like a circle. Think of a slinky that gets pulled up. So if you did this with a slinky somehow, this would be a region in which the torsion is very small. You're not moving very much. In a region like this, torsion is large. Now, I mentioned with the picture of the roller coaster that TBN frame moves moves as you move along the space curve, and this is just another example of that. So now we're going to calculate these vectors. So we start with the arc length parameterization, which is R sub s, here, and we take its first derivative. Now, because this is an arc length parameterization, the magnitude of this derivative, which would be its velocity, is 1. So we already have a unit vector. That unit vector is the tangent vector. Now we take the tangent vector, and from its first derivative, we're going to calculate the normal vector and the curvature. So here's the first derivative of that tangent vector. It's not necessarily a unit vector, so we separate it out as a magnitude and a unit vector. The magnitude is the curvature. Remember, the curvature varies with s, where it varies along the length of the curve, but I usually don't specify it, just to keep the notation simple. The unit vector created here is the normal vector n. So here's the equation for the derivative of the tangent vector. The derivative, the first derivative of the tangent vector equals the curvature times the normal vector. So we have the tangent vector, the normal vector, we need the binormal vector. We're going to take derivatives and make unit vectors again in a minute, but first we define the binormal vector as a cross product of the tangent and the normal. So that's your binormal vector. And now we have all three vectors. They're shown here on this particular curve. One thing to notice about these is that they're all orthogonal. In the written lectures I go through and show that the tangent vector is orthogonal to the normal vector, and of course by the cross product the binormal vector is orthogonal to both of them. So they're all orthogonal. They're all unit vectors, so they have magnitudes of 1. There's 3 of them. This is 3 space. They form what's called an ortho, because they're orthogonal, normal. So ortho, normal, basis for the space. The word normal is used several different ways in mathematics. Normal can mean a verb. It means that a vector or a line is at right angles to a plane. It's also used as the name of the vector that is normal to a plane or to a curve, as in this case. And normal also means that its magnitude is 1, that the magnitude of something is 1. So if you have an expression and you normalize it, it means you divide by the magnitude so that you have an expression that has a magnitude of 1. So that's a lot of different uses for the word normal. But this is called an orthonormal basis, because the 3 vectors are orthogonal, and normal because they're each unit vectors. Now we take that binormal vector and look at its first derivative. It's, again, not necessarily a unit vector, so we separate it out as magnitude and unit vector. This magnitude is the torsion, and it's written with the Greek letter tau, and it's customary to write the torsion as minus tau, right? By the way, torsion can be positive or negative, but curvature is always positive. Now the unit vector that we create here, the one that's in green, is the same normal vector that was created from the first derivative of the tangent. So you see we kind of come full circle on making these vectors. And here's the equation for the first derivative of the binormal vector. The binormal vector equals minus tau times the normal vector. And here we have the normal vector, which, because of the cross product and a few extra steps, we can write as b cross t. And now take the derivative of this vector. So again, we're just taking all these successive derivatives, and we take the derivative of the cross product, we get b prime cross t plus b cross t prime. But from the previous slides, you know that b prime is minus tau times n, and t prime is kappa n, curvature times the curvature multiplying the normal vector. These, of course, are vectors. Right. So substituting that, we have minus tau in here for the b prime and the kappa n for the t prime. Factoring out the curvature and the torsion, then we look at these cross products and we can simplify them again by using cross products. And this is all done in the written lecture notes, but if you can just get here a sense of how it's done, then I think that will sort of clear up the forest and the trees problem in making these calculations. So here's what we end up with. The first derivative of the normal vector equals torsion times the binormal minus curvature times the tangent. Now I'm listing here the Frenet-Serre equations. All these are is a listing of the equations that we just derived. How did that happen? Okay, the first derivative of the tangent equals the curvature times the normal. The first derivative of the normal equals torsion times the binormal minus curvature times tangent. And the first derivative of the binormal is the negative torsion times the normal. And it's easier to write it in a matrix form. And this matrix, you can see here, is fairly easy to remember. It's called a skew symmetric matrix. It's symmetric except for the sign changes. So I have a kappa here, a curvature minus kappa here, tau here, and a minus tau here. It's very handy to write this. This helps you remember the equations.